Hello friends, now we discuss how can we find the particular integral if in the linear differential equation with constant coefficient q is of the form sin ax or cos ax and f minus a square not equal to 0. How can we find the particular integral if in the nth order linear differential equation with constant coefficient the right hand side is of the form sin ax or cos ax and f minus a square not equal to 0. You know that what is the linear differential equation with constant coefficient? So linear differential equation with constant coefficient is dny by dxn plus p1 dn minus 1 y by dxn minus 1 plus p2 dn minus 2 y by dxn minus 2 and so on plus pn y is equal to q. You know that this is the linear differential equation with constant coefficient. This is the nth order linear differential equation with constant coefficient where p1, p2, pn these are the constants and q is either equal to sin ax or cos ax. How can we find the particular integral if this q is of the form sin ax or cos ax? So first we find the formula for finding the particular integral if q is of the form sin ax or cos ax. So first we find here, suppose first order derivative of sin ax. We know that d is equal to d by dx. So first we find derivative of sin ax, first derivative. So this is, we know that cos ax and a. This is the first order derivative of sin ax. Now we find again second order derivative of sin ax. So we differentiate this cos ax, a is the constant here, and differentiation of cos ax is minus a sin ax. So this is the second order derivative of sin ax. This is equal to minus a square sin ax. Now again we differentiate sin ax with respect to x and find the third order derivative. So third order derivative will be minus a cube cos ax. Now again we differentiate sin ax and get fourth order derivative. So the fourth order derivative is here a to the power 4 sin ax. And a to the power 4 sin x, ax can be also written as minus a square whole square sin ax. You know that here first we find the first order derivative of sin ax with respect to x, we get a cos ax. Again we find the second order derivative of sin ax, this will be minus a square sin ax. Now we again differentiate sin ax and get the third order derivative minus a cube cos ax. Similarly again we differentiate sin ax and find the fourth order derivative which is equal to a to the power 4 sin ax. And a to the power 4 can be written as minus a square whole power 2 sin ax. Now again we differentiate, get fifth derivative of sin x. So this a to the power 4 becomes a to the power 5 and this sin ax is cos ax. Now again we differentiate sin ax and get second order derivative. So this will be a to the power 6 minus times sin ax. And this minus a to the power 6 can be also written as minus a square whole cube sin ax. So you can see here this is equal to, you can see here this is equal to minus a square power 1 sin ax. You can see that when we differentiate sin ax 2 times we get minus a square to the power 1 sin ax. When we differentiate sin ax 4 times we get minus a square whole square sin ax. When we differentiate sin ax 6 times, we get minus a square whole cube sin ax. So in general, when we differentiate sin ax 2n times, we get here. Now in general, when we differentiate sin ax 2n times, we get here minus a square whole power n sin ax. You can see here is 2 and here is 1, here is 4, here is 2 and here is 6 and there is 3. So this is the half of 6 and this power is half of 4 and this power 1 is half of 2. So when we take here 2n, there will be half, so this is n here. Now this d to the power 2n can be also written as d square whole power n sin ax is equal to minus a square whole power n sin ax. Now if you put d square whole power n, this is the function of t square, so this can be written as f d square sin ax, and here in the right hand side this can be written as minus a square sin ax, where f d square, this is equal to d square whole power n, and f minus a square, this is equal to minus a square whole power n. Now we multiply both sides by the operator 1 upon fd square. So we get, now we multiply both the sides by 1 upon fd square. So we get here 1 upon fd square times fd square sin ax, and in the right hand side 1 upon ft square times f minus a square sin ax. You know that fd square, this is the differential operator, and 1 upon fd square, this is the integral operator. So both are the reciprocal to each other, so these will be cancelled out. So here we get only sin ax, and f minus a square, this is the constant, so we will take this outside the integral operator. So here we write f minus a square times 1 upon d square of sin ax. So this f minus a square divide in both the sides, so we get here f minus a square times sin ax is equal to 1 upon fd square sin ax. So you know that if we find the particular integral of sin ax, we substitute minus a square in place of d square, where f minus a square not equal to 0. So this is the formula for finding the particular integral of sin ax. You have to learn this. If we find the particular integral of sin ax, we put minus a square in place of d square. Similarly, we find the formula for the particular integral of cos ax. This is equal to 1 upon f minus a square of cos ax. This is the formula for finding particular integral of cos ax, where the limit is f minus a square not equal to 0. Now we take some example. Have we take some example? This is the second order linear differential equation with constant coefficient. You know that this is the second order linear differential equation with constant coefficient. So for finding the solution of this differential equation, we can write this as d2y plus y is equal to sin 2x. You know that capital D is equal to d by dx, and d square, this is equal to d2 by dx2. So this d2y by dx2 can be also written as d square y plus y is equal to sin 2x. Now we taking common here y, so we get d square plus 1y is equal to sin 2x. Now we find the complementary function. So for finding complementary function, first we write here auxiliary equation. So auxiliary equation for finding auxiliary equation, we replace m in place of d. So we get this is m square plus 1 equal to 0, and m square plus 1 equal to 0, this can be written as m square equal to minus 1. So m is equal to root of minus 1, and you know that m is equal to I. So this is equal to 0 plus I. So this can be written as alpha plus I beta. So here alpha is equal to 0 and beta is equal to 1. So the roots of the auxiliary equation are imaginary, and alpha is equal to 0 and beta is equal to 1. So we write here complementary function, that is e to the power alpha x c1 times cot beta x plus c2 times sin beta x. We put value of alpha and beta and get the complementary function. So e to the power 0x c1 cos x plus c2 sin x, because beta is here 1. So this e to the power 0 is 1. So the complementary function is c1 cos x plus c2 sin x. Now we find the particular integral of q. So for finding particular integral, this can be written as 1 upon fd. This is equal to fd square y is equal to sin 2x. So fd square is here d square plus 1 and sin 2x. You know that when we find the particular integral of sin ax, we replace minus a square in place of d square, and a is here sin 2x. You know that the particular integral of 1 upon particular integral of sin ax, we replace minus a square in place of d square. Here a is 2. So in place of, we write here d square is equal to minus a square, and a is 2 here, so this will be minus 4. So minus 4 plus 1, this is sin 2x, minus 4 plus 1, this is minus 3, so this is minus 1 upon 3 sin 2x. This is the particular integral. Now we find the general solution. So the general solution of given second order linear differential equation with constant coefficients is y is equal to complementary function plus particular integral. So complementary function is c1 cos x plus c2 sin x, and particular integral is minus 1 upon 3 sin 2x. So this is the solution of the second order linear differential equation with constant coefficient. Now we take another example.